Welcome. In this session, we'll state the KKT conditions for a linear inequality constrained optimization problem, and we'll discuss each one of these. Let's recall the Lagrange function, which has a vector argument, and for inequality constraints, we'll use the symbol lambda to represent these, and we're going to define that as being our objective function plus, we can say, the dot product between the Lagrange multipliers and the property function, which in this case is the constraint matrix times the vector argument minus a constraint vector. And we will define a KKT point. This is a point, this is a widely used term, a KKT point, and we'll put a hat over it for the time being. And we'll define this as satisfying four conditions. One is that associated with this is that there exists a set of Lagrange multipliers, and there has to be one Lagrange multiplier for every one of these constraints, such that every Lagrange multiplier is non-negative. Some definitions will say a KKT point and an associated set of Lagrange multipliers. We'll put that as a separate condition. The second condition is that the point that we pick has to be feasible. That is, it has to be in the feasible set of all of those, in this case, linear constraints. The third requirement, the third part of point W hat being a KKT point, is that it's a stationary point of the Lagrange function. And when we differentiate the Lagrange function, that means that we have the symmetric positive semi-definite matrix K times the KKT point plus the objective vector plus the transpose of the constraint matrix times the Lagrange multipliers, and that has to equal 0. So this is saying that the KKT point and its associated Lagrange multipliers must together be a stationary point of the Lagrange function. And the fourth requirement, fourth part of the definition, is that the dot product, that's of a hat, the dot product of the Lagrange multipliers and the constraints must be equal to 0. So in English, we'll have terms for this. So we'll call this one dual feasible. And dual feasible means simply that the Lagrange multipliers associated with the KKT point all have to be non-negative. They might be 0, but generally they're 0 or they're positive. This means that the KKT point has to satisfy the linear inequality constraints. And that's what we explored in the previous sessions for this lecture. So we'll refer to that as being primal feasible. This third is saying that it has to be stationary. And this fourth one is a more interesting one. This is called complementary slackness. complementary slackness. And we'll be exploring this idea of slackness much later in further sessions and in a different context. For now, complementary slackness means this, is that let's unpack that, is that what that says is, so let's say condition 4. Condition 4 is, that's saying that if I take the ith Lagrange multiplier for this problem, and now I simply multiply it by a scalar value, so that would be if I take the ith one form of this matrix times the KKT point and subtract the ith entry of the constraint vector, let's put parentheses there, that has to be equal to 0. And what we'll observe, if there are two conditions for this, is that there's actually a binary choice. If the Lagrange multiplier is 0, it doesn't matter whether this condition is satisfied or not. And if the Lagrange multiplier is non-zero, it says this condition must be satisfied as an equality. Now let's think for a moment about two situations that happened in previous sessions. In one case, we had the minimizer being on the boundary of two constraints. And in those cases, those were satisfied as equalities. And so without actually going through the computation, we can identify that if that occurred, then that means that each of these is 0, and we would suspect that these Lagrange multipliers might be non-zero, and if they're non-zero and they're dual feasible, then they might be strictly positive numbers. And then in one situation that we had our feasible set looked like this, and we had an objective function with contours like that, and it was a point just such as that. So in this case, we knew that it was on the boundary of one constraint, which meant that this equality was satisfied, and that might be a positive number. And then it was inside, it was an interior point for the feasible set of another constraint. And in that case, this was not satisfied. It wasn't an equality. And so for that one, the Lagrange multiplier had to be equal to 0. So what we'll do in a subsequent set of sessions is we're going to go through the geometry of these KKT points and start to examine and explore how these interact. What does complementary slackness mean? How does it interact with feasibility, and how it interacts with stationarity? Let's list a few of the methods that can be used with KKT points to solve a constrained optimization problem. The one that we'll use mainly is a specific problem solution. That is, we'll analyze the KKT points and we'll see what we can do with the KKT conditions. Another method is called active sets, and in this method what you try to do is you try to establish at a KKT point which constraints are active and which are not. That will lead you to the next iteration. A penalty method is a way to change the inequalities so that they turn into a problem in unconstrained optimization. Closely related to that is a barrier method. That changes an equality into an unconstrained optimization. These methods can be combined, and they can also be combined with some active set methods. A common method for certain problems that we'll examine later on in further sessions are sequential methods, and what these do is they break the problem into simpler pieces and then iteratively solve each one of those. So let's think now about some of the implications. In this course, we'll use the KKT points to determine whether or not a problem can be solved at all. We'll use them to select specific solutions from a feasible set. We'll use them to understand regularization, which is an important part of nonlinear data analysis, and we'll also use it to understand support vector machines, which are a method for machine learning. So what have we gained from this? Well, we now know how to express a linear inequality. We understand that linear equalities together describe a convex set. A feasible point is a point satisfying every inequality, and a KKT condition is necessary and sufficient for satisfaction of a linear inequality for a quadratic objective function.